let's go ahead and get started on this. So here's the first question, okay? And what I'm going to do is I'm just going to put the question up here on the video, and then I'll pause the video for a minute, give you guys some time to work it, and then we'll talk about it, and I will video record that part, okay? So here's the first question, and I told you there was going to be a Hess's Law type thing on the test, so you need to remember how to do Hess's Law. And I think hopefully you can do this one fairly easily. It just involves some rearranging here, okay? Okay, so let's go ahead and talk about this. So what do we think we might need to do on this one? What's our strategy here? Okay, well we have to figure out how to combine these top three equations in order to make it look like the one at the bottom, okay? Now, this one's a little bit tricky. The problem is there's a lot of like N and O and NO and NO2 and all of that, so it's kind of hard to keep straight. But what I like to do is kind of just pay attention to what I need on which side of the equation, right? So for example, the NO needs to end up on the product side, okay? So any equation that has NO on the product side, that's probably a good place for it to be, okay? So this first equation is probably okay. Now we may come back to that in a minute, but let's take a look at the other two. The second equation right here, the NO is on the reactant side. That's probably not good, okay? So we probably need to flip that one, plus the NO2 here needs to be on this side. But you might notice something here. We only need 1 mole of NO2, right, in the final equation. And we need 3 moles of NO. If we add the 2 moles of NO from up here to the 2 moles of NO from down here, that's going to give us 4. So what can we maybe do to that second equation to fix that? Okay, so if we multiply this by 1/2 and flip it, if we do those two things, I think that's going to help us out, okay? So I have another screen here. I guess I'll just rewrite this. It's kind of a pain. So we've got N2. I'm not going to write the states of matter because they're all gases. Plus O2 yields NO. Is it 2NO? And then the delta H here is equal to, thank you, 180.7. So then the way we're going to rewrite the second equation here is we're going to have NO2 yields NO plus 1/2 O2. I know that's a little bit weird, but this is going to help us. So then what we'd have to do to our delta H here, okay, because our delta H is originally negative 113.1. Now we flipped this thing, so what's that going to do to the sign? It's going to change to positive, okay? And then we also have to multiply this by 1/2, or, you know, divide by 2, however you want to look at it. And I'm ashamed that I can't do that in my head. 56.55. So this should be plus 56.55 here. These are both kilojoules. Okay, and then let's take a look at the last equation. We really haven't talked about that one yet. I think that one's okay as written because the N2O is where it's supposed to be. But again, we have 2 moles of it instead of 1. So we need to do the same thing to the bottom. Here we need to multiply by 1/2. Okay, so once we do that, we end up with N2O yields N2 plus 1/2 O2. Okay, and the delta H for this one, again, we have to multiply by 1/2 as well. Negative 81.6, thank you. Okay, so then when we add all this together, we just want to check and make sure it all works out. The 1/2 O2 plus the 1/2 O2 gives us a mole of O2, which cancels out this mole of O2 over here. We add the 2NO to the 1NO, that's good, and then the N2 also cancels. All right, so then I think we've got what we need here. NO2 plus N2O, that's confusing, yields 3NO. Is that our equation? Yep. So then all you have to do at the end, because we added the equations together, you just add up the delta H's as well. And the number we should get here should be 155.65, and if we're rounding this to sig figs, 155.6 correct, I guess. Kilojoules. I mean, technically, because it's an even number, you're supposed to round down. If it's an odd number, you round up. I never really taught you that rule because I don't think it's important. If you round it up, well, yeah, but if there's nothing after the 5, then it depends on whether it's even or odd, because 5 is right in the middle, so... Yeah, I know. It's just, if you round up once, round down the next time so the universe doesn't explode or something. I don't know. Okay. Next question. Calculate the standard enthalpy change for the following reaction. And I'm giving you some heats of formation here. Okay, so notice that extra information. Okay, so let's go ahead and talk about this one. What you have to remember on this one is to find the delta H of a reaction here when you're given the heats of formation. Your delta H is going to be equal to basically products minus reactants. Okay, now I'm simplifying the equation a little bit when I write it this way. You have to take the sum of all of the delta H formation on the product side minus the sum of everything on the reactant side. Now in this particular equation, we only have one on each side that we need to worry about. And the reason for that is O2, its delta H of formation is 0. Okay, that's kind of the baseline right there, is the element in its standard state. Okay, and so we don't have to worry about the O2, we just need to worry about the SO3 and the SO2. All right, so when you set this up, the delta H of the product, which is the SO3, is negative 395.2. Okay, so the overall delta H here is going to be negative 395.2, and that's, we're worrying about units here, it's kilojoules per mole. We multiply that by 2 because there's a coefficient 2 in front of it in the equation, and then we subtract that from the reactants. And the reactants here, well, the only reactant we need to worry about is the SO2, and that is negative 296.9 times 2, now I was lazy with my units there, kilojoules per mole times 2 moles. Okay, so that's just going to give us kilojoules at the end once we figure this out. And the number I'm getting, and just correct me if I got the wrong number here, I'm getting 196.6 kilojoules. Is that right? Okay. So there's your answer for your delta H. Okay. All right, next question. For a certain chemical reaction, delta H, it's giving us the delta H and the delta S. Okay, so then we've got several questions that go along with that, and I kind of like this one because it has a bunch of different things in it. So go ahead and take a look at this one for a minute, and then we'll talk about it. Okay, let's go ahead and talk about this one. So I'm gonna write the answers on the next screen. I know that's a little annoying, but the reason I'm doing that is so that if you're watching the video, you can, if you want to, you can just go right to that answer screen and you can see all the answers right there. Hopefully that helps. So is the reaction endothermic or exothermic is the first question. That should be pretty easy at this point, right? It is exothermic because the delta H is negative, okay? So A, exothermic. Okay, second question, does the reaction lead to an increase or decrease in the disorder of the system? And again, just looking at the sign on the delta S should tell us what we need to know there. Is there going to be an increase or a decrease in the disorder? Okay, there's actually a decrease in disorder here, okay? And again, that's just because the delta S is negative. If the delta S is positive, that means the disorder is increasing. Okay. C is the only one that really involves a calculation. You have to calculate the delta G, and that's going to come from the equation delta G equals delta H minus T times delta S. Okay? So then when you plug in those numbers, there's only one thing that makes this even remotely difficult here, and that's watching your units. So 35.4 kilojoules is our delta H. Okay? Then we have to subtract the 298 K, which is the temperature, times the delta S. But because the delta H is in kilojoules, you have to change one or the other. Okay, it doesn't really matter which one you change, but you have to change one or the other. And the reason I'm changing the delta S is because usually delta G gets reported in kilojoules, so then I don't have to convert at the end. So, but whichever way you want to do it. Okay. This is going to be negative 0.0855 kilojoules per per Kelvin. Sorry, I ran out of room there. Okay, once you multiply all that together, you should get a delta G of, now this is at 298K, so if I want to, I can put that little circle there, right, because that just means we're at standard temperature. And I'm going to assume standard pressure because they didn't say otherwise. So then we're going to end up with negative 9.9 kilojoules, I think is what I was getting. Is that what you guys were getting on that one? Okay. And the reason I rounded to 9.9 is because we're doing a subtraction here between the delta H and the T delta S. The delta H only has one decimal, or one place after the decimal, so then when you're doing a subtraction, you would have to round to one place after the decimal. Okay. Again, not a huge deal, but you got to kind of watch out for the sig figs, just so you're not off by more than one. So there's our delta G for this one, and then that should help us to answer part D here, which is asking, oops, went the wrong way. Is the reaction spontaneous at 298K? Because the delta G is negative, the answer is yes. Okay? Alright, so that's that one. On to the next one. Use the delta H formation data and S data to calculate the value of delta G for the following reaction. And then how is the delta G expected to vary with increasing temperature? Okay, let's go through this one. Oops, wrong thing. Let's go through this one quickly. Alright, so a couple of things you have to do here. First of all, you'd have to figure out your delta H formation, okay? Or, sorry, just your delta H for this reaction. Now, kind of the nice thing about this one is the H2 and the F2 both have a delta H formation of 0, right? Because those are the elements in their standard state. So the only thing that you have to do here is multiply the heat of formation of the HF by 2, okay? So our delta H for this one is going to be negative 537.22, I believe. And stop me if I have miscalculated, because that's possible. And then our delta S for this one, after you take products minus reactants here, and you have to multiply the HF by 2 because of the coefficient 2, you should get, I was getting 9.24 joules per Kelvin. Does that sound like what you guys were getting on that one? No. Okay, let me double check there. So, 173.51 times 2 minus the F2, which is 202.7, minus the H2, which is 130.58. Yep, I calculated that wrong. 13.74. Okay. 13.74 joules per Kelvin. Okay, so then when you do your delta G equals delta H minus T times delta S, then you should get, I'm going to trust you guys for your answer on this one because mine's going to be off now. Now the one thing you have to, actually I can calculate this quickly, negative 537.22 minus 298 times 0.01374. So you get negative 541.31, and that's kilojoules. Okay, now, we should be able to answer the second part of this question very quickly. How is the delta G for the reaction expected to vary with increasing temperature? Okay, so with increasing temperature, it is going to do something, right? Okay. So as we increase the temperature, that's going to increase this expression right here, okay? But that's actually going to make it even more negative, right? Because the S is positive, so this is A. It's going to decrease or become more negative, maybe is a good way to say that, as we increase the temperature, okay? Oh, yeah. Don't leave until you've given me your quizzes.